Hello, everybody. My name is Masood Olia, and I'm a professor of engineering at Wentworth University. And I'm here with a problem related to the subject of mechanics of material and to the topic of factor of safety and shear stress and failure due to shear stress. Uh, so this is a very simple problem, which kind of combines the concept that you've learned in the statics course and the simple definition of shear stress. So as we read the problem says six nails are used to hold the hanger at A. So basically, if you look at here, this is what you see. If you look at the side view, so this is the hanger at A, and let's say there are six nails like this in this orientation. So those are the six nails that are holding this, kind of like that. And that's your beam. All right. Determine the minimum required diameter of each nail to the nearest, I should say inches here. If it's made of material having a failure of shear stress of 16 KSI. So in other words, the nails are made of the material for which they would fail at 16 KSI. Now, you have to understand that the failure stress doesn't have to be necessarily a failure stress. It could be the yield or it could be the ultimate. But in this case, we take it as a failure. And then it says use a factor of safety of 2, which is relatively high for kind of like static loading problems. All right. So basically, the way you apply this factor of safety, and then I'll come back to the objective here, which is figuring out the diameter in a minute. So we know that factor of safety, basically the load or the stress that causes failure, the ratio of failure divided by what we call allowable, what we want to use. So we want to be safe. So therefore, tau allowable would be tau failure, which is 16 KSI, and then we put the factor of safety of 2 there. So this is basically reducing our stress, what we want to have in each nail here to be 8 KSI. 8 KSI means 8,000 PSI. So right now, our allowable stress is 8 KSI or 8,000 PSI. KSI means kilo PSI. Remember, what we are trying to find is the minimum required diameter of each nail. So D is what we're looking for. And we know that the definition of the shear stress is shear load divided by what we call shear area. So if we have tau, and we want to find the area for which from the area then we can determine the diameter, then we need to figure out what is the shear load acting on each of these nails. So that comes from the statics. We need to draw a free body diagram for this beam subjected to this triangular loading. So we know that there would be a reaction here, call it B sub Y, and call this A sub Y. Remember, this is not fixed into this beam. It's just one reaction that we get here. And there is obviously no X component of reaction there. All right. So we can change this distributed load. Remember, we can change it to a concentrated load. That concentrated load is equal to the area of this shape, which is 1/2 of the base, which is 9 feet, right? So this is the area, basically. Times what? Times the height, which is 300 pounds per foot. And that would be 2,700 divided by 2. That's 1,350 pounds. You can see feet and feet cancel. All right. So where would we put that distributed, the concentrated load, replacing this distributed load? Remember, it has to go through the centroid of a triangle. Centroid of a triangle, as we know, is 1/3 of the base from the right angle side or 2/3 from the other side, right? So 1/3 of 9 is 3. So that would be 3 feet, and this side would be 6 feet. So let's put the 1,350 pound load here. And then, as you know, this is really a trivial situation. We have two unknowns and two equations. The two equations are sum of the forces in y equals 0 and sum of the moment equals 0. Obviously, if you take moment about B and say if we pick clockwise to be positive, then we can find AY, and that's all we need. AY will determine what's going on here at these 6 nails at the hanger. So look, the moment of AY about B is AY times 9, and the moment of the 1350, and that's going positive because it's going clockwise. 1350 about B going counterclockwise times 6. So we solve for AY, which should come out to be exactly 900 pounds. All right. So now look what we're going to do here. I can redraw it here for you. So these are the 6 nails. And this is the reaction that we just found, the 900 AY. So we're going to have to divide that evenly to 6 shear loads, right? 6 of these. So basically, we are saying 6V must be equal to what? Equal to 900. Therefore, V must be equal to 150 pounds. So now you have this value, you have tau, then you can find the area. So let's go and do that. So tau, remember, after we applied the factor of safety, right? Tau, that's the tau allowable, V divided by area. So you can see that shear area is going to be, so A sub S means shear area, by the way. Maybe I forgot to mention that. And I'll tell you what that shear area is in a second. It's related to the diameter of the nail, each nail. So V divided by tau allowable. So if you take 150, right, pound, and divide it by 8,000 PSI means what? Pound per inch squared. So let's see, what is 150 divided by 150 divided by 8,000 becomes 0.01875, and you see the unit would be inches squared because pound and pound cancel, inches squared goes up, right, into the numerator. So now, what is the shear area? So if one nail is like that, this is the shear area, guys, the area where this shear load is acting, right? So area of a circle is what? In terms of diameter, would be pi over 4 diameter square, or pi r squared if you want to use the radius. But we want to find the diameter, obviously. So now we go ahead and say, okay, A sub S is pi over 4 diameter squared. Therefore, just rearrange the equation and solve for diameter. So diameter becomes the square root of 4 times AS divided by pi. So square root of 4 times 0.01875 inches squared divided by pi. Remember, the unit is inches squared inside the radical. Let's say it should be about 1.1545 inches. So at minimum, you need the diameter of 0.1545. So very simple problem combining the concept of statics, factor of safety, and the basic definition of what shear stress here, right? I hope you enjoyed this video. As always, I appreciate if you like the video and also subscribe to my channel. I'll see you soon. Thank you.